We are going to start the PhD defense of Lucas Squillante. Essentially, the rules are the following. We are going to start sharp at 8 a.m. Then Lucas will have about 40 minutes to up to 60 minutes for making the presentation. Then the committee will be arguing the candidate up to 30 minutes, each member of the committee. Okay? I want to welcome everybody. Vou falar agora em português. Bom dia a todos, bem-vindos, bem-vindas. Nós vamos começar aqui a apresentação do Lucas em respeito ao nosso convidado da África do Sul. Eu vou falar obviamente em inglês, a apresentação vai ser em inglês, as discussões serão em inglês. E essencialmente a gente vai começar às 8 horas em ponto, de 40 a 60 minutos para a apresentação e até 30 minutos para discussão, para a arguição de cada membro do comitê, tá bom? Lucas, the stage is yours, please.
Thank you very much, Professor. So I'm going to start now my presentation regarding the work I have been developing the last 4 years. Professor Mariana is my advisor. So the title is The Organizer Parameter Applied to Critical Phenomena and Experimental Investigations of Related Phenomena in Molecular Conductors. Essentially, this represents a symbiosis between theory and experiments. And I would like to emphasize here that we didn't stick to a single problem here, as the committee of the members of the committee can be seen in the PhD thesis. So first, I'm going to start the outline of my presentation with some motivation and goals. Then, regarding the theoretical section, I'm going to cover the following aspects. I'm going to talk about the Organizer parameter applied to critical phenomena, why it's important to use the Organizer parameter to explore the vicinity of quantum critical points and finite T critical points. I'm going to talk about the Bernoulli paramagnet, well known from textbooks, and their mutual interactions and the consequences of taking these interactions into account in terms of zero-field quantum phase transitions. Then I'm going to talk about the elastocaloric effect induced adiabatic magnetization, which was our proposal we made in the frame of my PhD thesis, and how to optimize caloric effects in terms of entropy arguments. And last, I'm going to talk about the connection we have made, a contribution to cosmology with well-established concepts of condensed matter physics. Regarding the experimental section, I'm going to make a brief review of the mode transition. I'm going to talk about the molecular conductors of the TMTTF family, the Mott-Hubbard ferroelectric phase, what are we interested in measuring and why, and I'm going to talk about the solid-state physics laboratory, the infrastructure we have here to explore this, and I'm going to end this section with the experimental results. And, of course, at the end, I'm going to present some conclusions. So the motivations, first, the motivation for the experimental part is to explore the possible multiferroic magnetoelectric character of the Fabry salts. We're interested in exploring if the chart order phase is indeed magnetoelectric or multiferroic. This is an open question in the literature, and that's what we have focused on the experimental part. In the theoretical part, we have 3 pillars. The first one is to unveil exotic manifestation of matter at low temperatures, to propose key ingredients in terms of material design to maximize caloric effects. This is to aim in technological applications, how to synthesize materials that are good candidates for performing caloric effects and can be used as cooling devices. And last but not least, the contribution to cosmology in terms of well-established concepts to provide a new interpretation or a new picture of the universe expansion in terms of the condensed matter physics. So first let's start the theoretical section and the Organizer parameter applied to critical phenomena. First, it's well known in the literature that both finite temperature and quantum critical point play a key role in thermodynamics. Here, regarding the quantum critical point, we have a schematic temperature versus tuning parameter G phase diagram. We have here that the tuning parameter can be pressure, magnetic field, doping. Then you have an order phase separated by a quantum critical point at a finite value of the tuning parameter to another phase. It can be either order or disorder. And we have here the proposed zero field quantum critical point. So I'm going to focus here where the tuning parameter here is magnetic field. Okay? So here we have the dashed line showing the disappearance of an energy scale when we cross the critical point. And here, the one dimension is in model the transverse field as a canonical example of a quantum phase transition. So in order to explore, in particular, field-induced quantum critical points, a very proper tool is the so-called Grunizen parameter. Before discussing the magnetic version of the Grunizen parameter, I'm going to discuss the thermodynamic version. The Grunizen parameter, or the Grunizen ratio, is defined as the ratio between thermal expansion and specific heat. Essentially, it embodies how entropy changes as a function of pressure and temperature. In this case, G is pressure, and this is associated with the barocaloric effect. That is, if I change pressure diabatically, there is a temperature variation in response to that pressure variation in order for the entropy to be constant. So in the magnetic case, where the tuning parameter is magnetic field, we have the same, but now we call it the magnetic Grunizen parameter. I'm going to discuss this in terms of gamma mag to avoid long words. And this is essentially how entropy varies with respect to the magnetic field and temperature, and this quantifies the so-called magnetocaloric effect, which is usually employed in diabatic demagnetization to achieve millikelvin temperatures. Okay, so this gamma mag is well known in the literature to probe quantum critical points induced by magnetic fields. But there are three conditions that must be satisfied in order to do so. First one, this parameter must diverge for t going to 0, and there should be a sign change of the magnetic Grunizen parameter upon crossing BC, which is the critical parameter, which can be either a finite value of field or 0. And a typical T over B minus B over BC to power epsilon scaling, where A epsilon is a scale parameter. Okay? So if these three conditions are fulfilled, then we have probe in terms of gamma mag, a quantum critical point or quantum phase transition. That's the focus of this part. So it's well known in the literature that we have schematic, for example, temperature versus pressure, phase diagrams, we have gas, we have liquid, solid, we have here a first order transition line that ends in a second order critical point. This can be extended to a real system, the quasi-bidimensional kappa B DTTF2X system, where we have paramagnetic insulator, antiparamagnetic insulator, superconductor metal. Then we have a first order transition line that also ends in a second order critical point. So this is for finite temperature, just to show you that the Grunizen ratio, it's well established that there is an enhancement of this quantity close to finite temperature critical points, because it's intrinsic that entropy is accumulated in this region due to the competition of phases close to the critical point. So this is well established in the literature, and now I'm going to focus on the magnetic Grunizen parameter. As I said, the one-dimensionalism model under transverse magnetic field is the canonical example of a quantum phase transition. And then we can calculate gamma mag for this case. So consider we have a chain of spins in a particular direction. We have the J primes, the exchange interaction between them, and we have a transverse magnetic field. So we have the Hamiltonian. The Hamiltonian incorporates G prime, it incorporates the spin operators in the z-axis, for instance, Z, S, Z, I, S, Z, I plus 1 between nearest neighbors. And the magnetic term here is associated to a transverse field in the direction that is, of course, transverse, where the spins are set. So the gamma mag was already calculated for this case. When the magnetic energy equiparates, or it's equal to the J prime, we have a quantum phase transition from a ferromagnet to a quantum paramagnet. Okay? And this magnetic Grunizen parameter, as you can see, if these quantities are equal, this diverges. So this is the canonical example. Great. So now let's talk about the well-known from textbooks Brillouin paramagnet and the mutual interactions. It's well known that Brillouin paramagnet is a non-interacting model, magnetic model. It only incorporates the probabilities of the spins or the magnetic moments to be aligned in a parallel or an anti-parallel direction with the field. So this is a Boltzmann probability distribution. It just depends on the magnetic field and temperature. And then with these probabilities we can calculate analytically the entropy, and then we can calculate an expression for each which depends on two terms. Of course, if we plot this, the entropy as a function of temperature, for instance, we can see that the entropy should go to 0 as t goes to 0, because the third law of thermodynamics is obeyed. And then at high temperatures, we have that the entropy is constant, Kb ln2, because we have equal probabilities of the two states to be achieved. But here we have a little problem, because if we consider zero magnetic field applied, what we have is that the hyperbolic tangent of 0 is 0, and then the hyperbolic cosine of 0 is 1. So we have that the entropy is not temperature dependent in this case. So it violates the third law of thermodynamics. So how can we fix that? I'm going to go back to this soon. Okay? So this is problem we have, this is the core of this discussion. First of all, I would like to mention that for the Brillouin paramagnet we have access to the partition function, which depends on the summation of the magnetic quantum number from minus j to j, whereas j is the total angular momentum in this case. And then we have a partition function which depends on the lambda factor, Bohr magneton, angular momentum, magnetic field, Boltzmann constant, and temperature. And then, if we have the partition function, we are able to calculate the free energy, minus kBt ln z. And with the free energy, we can calculate the entropy, equal to minus the derivative of the free energy as in respect to temperature. And then we can calculate the derivative of the entropy in respect to B and T, and we can calculate the magnetic potential per meter. So we have done this in the past, and this was the result for the Brillouin paramagnet 1 over B, which shows that for B equals 0, first of all, it does not depend on temperature, as you can see, but for B equals 0, we have a divergence and sign change. Okay? And of course, for the magnetization, we have a step-like when we switch the field, and this results was my contribution to this paper that was published in Physical Review B. It was the first paper of my PhD. So now I'm going to come back to that problem of the entropy when B equals 0. So it turns out that this is actually discussed in textbooks like Ashcroft, that when you have H equals 0, according to the simple theory, this would be constant and we don't have an agreement with the third law of thermodynamics. But how to solve this? In order to solve this, we have to incorporate the dipolar magnetic interactions, even though the system is non-interaction. Okay? So in order to do that, we consider that the dipolar magnetic energy, here in this case, depends on the vacuum permeability, the r to power 3, the distance between the spins, and if we agree that this term does not contribute much to the energy, it does depend on the modulus of their magnetic moments. So the idea is this is the magnetic energy. We can rewrite this in terms of a magnetic field, which is we call the local magnetic field, which is roughly 0.01 Tesla, considering a typical distance between magnetic moments of 5 angstroms. Just for a comparison, the Earth it's way this is way bigger than the Earth's magnetic field, and it's 9 times smaller than magnetic field of our refrigerator magnets, just for comparison. So, what is the take-home message here in this part? We have to, although we have a non-interacting system, we have to consider this, otherwise we don't have an agreement with the third law of thermodynamics. So now, if we consider that in the frame of zero field quantum phase transitions, that is, when I just switch the temperature to 0, closer to 0 as possible, then even though in the absence of external field, we will have a quantum critical point. So in this case, we have considered that now our system is not just under an external magnetic field, but it's under our resultant magnetic field, which depends in both the external magnetic field and the local magnetic field. Okay? And now, when we do this, the entropy, it can be rewritten by this form. And now, even though the external magnetic field is 0, we have a temperature-dependent entropy in this case. And of course, these mutual interactions have a particular energy associated with it. And as we decrease temperature, they become more and more relevant. And these mutual interactions are very important due to this part because it corrects the Brillouin model in terms of the third law of thermodynamics. But here lies the question. If in the literature is proposed that there are systems who present a genuine zero field quantum phase transition or quantum critical point, is it really 0 if we consider the local magnetic fields? I mean, Even though the external magnetic field is zero, we have intrinsically a local magnetic field because of the intrinsic dipolar interactions between the magnetic moments. So this resultant magnetic field will never be zero. So what is the impact of this in the context of zero field quantum phase transition? So that's the important part here. So in order to investigate that, we have used a real system of the literature with the beta ytterbium aluminium boron 4, where the magnetic moments come from the ytterbium atoms. They are typically in a distance between 3.5 angstroms of each other. And then it's described in the literature that the magnetic ionizing parameter, a function of temperature, it increases as we go to, as we decrease temperature and we decrease the magnetic field. So it seems that there is an enhancement of the magnetic ionizing parameter when T and B goes to zero. This would implicate in a zero field quantum critical point. So what we have done is what we have made use of this so-called quantum critical free energy, which comes from valence fluctuations, to incorporate the local magnetic field in this case, because of course in real systems we have the intrinsic magnetic interactions, and we have calculated the ionizing parameter with and without the local magnetic field to see what was the impact on that. First, we have done this, of course, employing the definition of gamma mag, and for the beryllium paramagnet, we can see that even though it does not depend on temperature, when we consider the local magnetic field, that divergence I have shown you before, it vanishes, it disappears, and just a sign change takes place. And the same happens for the real system beta ytterbium aluminium boron 4. This divergence, when the local magnetic field is not considered, disappears when you consider local magnetic moments or the local magnetic field. So this is just to show that when dealing with real systems, one should make use of the local or the effective magnetic field to discuss this to see if this is really a zero field quantum phase transition or critical point. Also, we have made use of gamma mag to connect this with the so-called temperature definition. That result I showed you before was one of the key results of this part. This is the second one. So we all know that the proposed in the literature that the 1 over T equals to the derivative of entropy in terms of the energy. In this case, the average magnetic energy. And then we have the entropy as a function of the average magnetic energy as this parabolic function, which defines a regime where the temperature is either positive when this derivative is positive, for instance on the left, but it also covers the possibility that temperatures must be negative, and because this derivative can be negative. And this positive temperature is associated with a parallel configuration between magnetic field and magnetic moments, while the negative temperature is associated with an antiparallel configuration. And I'm not talking about Celsius, negative Celsius degree, I'm talking to negative Kelvin, which it can be quite non-intuitive, okay? So by making use of this definition, we have made use for the beryllium paramagnet of the average magnetic moments, which depends on the number of the magnetic moments, of course, the magnetic field and temperature. And we have written this in terms of the average magnetic moment. And we have isolated, we have solved this for B as a function of T, because we know that gamma mag can be written in terms of the entropy derivatives, but it also can be written in terms of the temperature derivative in the respective field. So we made this derivative, B, derivative of B over T, which is exactly this to power minus 1, and making use of the result for the beryllium-like paramagnet, we have seen that temperature can now be defined with respect to the average magnetic moment. So if the average magnetic moment is positive, this means that the majority of spins are aligned in a parallel configuration to the field, so this is associated with a positive temperature. While this average magnetic moment is negative, this is associated that the magnetic moments are in an antiparallel configuration, so the temperature is negative. So we have unprecedentedly connected the magnetic ionizing parameter with the definition of temperature to show that the definition of temperature is encoded in the magnetic ionizing parameter and vice versa. Okay, this was another important result of this part. And the last part of this this work was associated to one of proposal of ours due to the so-called adiabatic magnetization. But do not confuse this with the adiabatic demagnetization, which is used, as I told you before, to cool systems in the range of millikelvin. So the idea was, what would happen when, okay, we know we have the local magnetic field in a paramagnetic insulating system. What would happen if we increase temperature adiabatically? Well, first, we always think about temperature as an exchange of heat, so how can we increase temperature without exchanging heat? So it sounds another, again, counterintuitive, but it can be done, and I will show you in the next slides. But what we have seen is that if we have, of course, the entropy as a function of temperature, we have this typical shape I have discussed with you before, but if you zoom in this region where the mutual interactions are, the relevance of the mutual interactions are in, I'm going to say this in another way, where the magnetic energy is comparable to the thermal energy, we can make a cycle process, which in turn we can increase temperature adiabatically, and in order for the system to remain its entropy constant, the spins must increase their projection in the z-axis in order to magnetize the system. Because we are increasing temperature, and in order to compensate this for the entropy to become constant, the system is magnetized. So this is the so-called adiabatic magnetization we have proposed. And this, we can calculate what is the variation of the local magnetic field in terms of the local magnetic field and the temperature of the starting and the end of process. Okay? So this gave us a nice publication in the frame of my PhD, which was published in Scientific Reports in 2020. And this is the main part in this section. Now I'm going to a different part, which is a natural continuation of that. You can see that first we have explored the Bernoulli paramagnet in the context of the published paper PRB. Then we have given a step forward to the scientific reports published regarding the mutual interactions in insulating paramagnets. And now we have explored this in more details on how to increase temperature adiabatically, and most important, how to detect this adiabatic magnetization experimentally. So first, we can make a brief review on thermodynamics of adiabatic temperature changes. The adiabatic compression, we can, for instance, assume that the variation of entropy depends on variation of temperature and pressure, and of course, in adiabatic character, the variation of entropy is zero. And then we can employ the thermodynamic relations, and then we can achieve this key expression, which connects the variation of temperature with the variation of pressure. So if you increase pressure, this dP is going to be positive, meaning that temperature should be increased in order to maintain the entropy constant. And if the pressure variation is negative, which means I'm reducing pressure or decompressing, the temperature must go down in order for the temperature to, for the entropy to remain constant. This is essentially the barocaloric effect I have discussed with you before. And of course, this can be rearranged and we can recover the Brunizing ratio I showed you before, which quantifies the barocaloric effect. But now, what if we decompose pressure into stress components? We can assume that the variation of entropy depends on temperature, and a tensor, a stress tensor, which incorporates all the possible applications of pressure, it essentially is 9, and then we can see how the system would behave if we, for instance, only assume we have an uniaxial compression. We're going to compress only in the x direction, for instance, which is this. So we have this, and analogously, we have achieved this, the relation between the variation of temperature and the stress tensor, which means that in this case there is a particular case, a particular situation, because negative d sigma means that you are compressing. This is well established in the literature. So if we compress this, which means this is negative, this is going to be positive because of this sign. And then if we compress, the temperature go up, and if decompress, temperature should go down. This, of course, adiabatically, otherwise this would not work. This made us to propose for the first time the so-called elastic Brunizing parameter, which quantifies the elastocaloric effect. That is, when we compress in a particular direction, a sample adiabatically in temperature is increased or decreased. Okay, so how would we detect the adiabatic magnetization? How would we increase temperature adiabatically? First, let's talk to the increase of temperature adiabatically. As I said, it sounds counterintuitively because every time we are exchanging heat with its surroundings, and we don't have a perfect vacuum, in order we don't have particles, and even though we have the temperature variation by radiation. And then how can we do this? We have our sample glued in epoxy to a movable sample plate, and we have this fixed sample plate. This movable sample plate is attached to a piezoelectric stack. So this is essentially a material that when I apply voltage, it has a distortion in its structure, meaning that I can control its compression and decompression when I employ an AC voltage here with a particular frequency. So if I put a signal there, it will make a movement like this. It will expand and compress in the frequency of the applied voltage. Okay? This is very important because if I tune this frequency to be very fast, in order that this is greater than the thermal relaxation rate of the sample, that is, there is a time scale where the sample exchanges heat with its surroundings. But if I compress and decompress it faster than it can exchange heat, then I have a window that I can have an adiabatic compression or decompression. And this has been done in the paper from the guys from the United States. And then we made use of this to propose that this can be used to increase temperature adiabatically, but how would we detect the adiabatic magnetization? We have proposed that we can use a nanosquid tip sensor. This is a work from the Israel group of Elitzeldov. They have a squid of nanometric scale that are able to capture variations of magnetic fields in the range of nanotesla. So here we have proposed this experimental setup to not only increase temperature adiabatically, which in turn gives rise to adiabatic magnetization, but also to detect the subtle effects. Okay? So this gives another interesting work, a nice publication in scientific reports. And then I'm going to talk about the next work associated with caloric effects. Okay? So it's well known that, as I mentioned, that the granizing parameter is important to explore critical phenomena or the proximity of critical points at finite temperatures or quantum critical points. It also quantifies caloric effects. And caloric effects are of interest because when we have these air conditions like in this room, we have toxic gas for the environment that are used to cool the system, but there is an interest in the community to generate more eco-friendly devices. So it's cheaper and it's green, and sometimes it can be more effective. So in the last few years, the discovery of large caloric effects in materials have been increasing because they have discovered large caloric effects in some particular systems. So we have, as I mentioned, the magnetocaloric effect is induced by magnetic field, the barocaloric effect is induced by pressure, the electrocaloric effect is induced by electric field, the elastocaloric is the stress components, and of course we have systems where we can perform more than one of these. They are called multicaloric. Okay? Usually in the literature, how to quantify if a material has a large or small caloric effects. Usually is how much the temperature is varied divided by how much you have to change the tuning parameter to achieve that variation of temperature. So, as I mentioned, the granizing parameter is also quantifies caloric effects, and there is additional information that can be extracted to this parameter because it's associated to the entropy, where this additional aspect is not covered in here. So the maximization of the electrocaloric effect near a critical point was already reported. So this we can see that close to the critical point, the variation of temperature is maximized. But what we have done is, by knowing that close to any finite temperature critical point, we have an intrinsic entropy accumulation, and that this entropy is crucial for determining if the caloric effect will be large or small. Then we have proposed a schematic temperature versus tuning parameter for any phase diagram showing a finite temperature critical point where we have above the critical point a middle line of a supercritical region, and below we have the first coexistence region, which is in the middle we have a first order transition line. So it doesn't matter if we have a paraelectric to ferroelectric phase transition, paramagnetic to ferromagnetic, insulated to metal. In this region, the entropy is going to be enhanced because of the competition of phases and more other ingredients I'm going to discuss. But essentially, we have discussed that in this region here, the border of this yellow circle is the boundary of easing to Landau-like regime. So there's this change of regime, and I have proposed that exactly here that the caloric effects will be maximized. And here we can see, for instance, that we have, for example, ferromagnetic system where you have dipoles separated by domain walls, and then if we pressurize this, there is an entropy increase because of the pressurization, which in turn is important for caloric effects. Okay? Great. So we have proposed, in terms of material design, if one could go to the lab and synthesize a particular material, what ingredients they would expect to have in their system in order to have an enhanced caloric effect, aiming for technological applications. So we have here some key ingredients we have proposed. First one is of course the coexistence region. Coexistence increases the entropy. We have the dipolar configurations. We have the presence of domain wall grain boundaries. We have the interfacial entropy associated with Maxwell-Wagner contributions. We have structural instability. We have spin ice entropy, which is a residual entropy in spin ice systems associated with two particular configurations. And of course, we have the proximity to the critical point. So if one would want to synthesize a material that is like the good candidate, our proposal was that they had to incorporate as many of these contributions as they can. So because the message here is the more entropy contributions, giant caloric effects will be achieved. Because if your entropy is higher, then when you vary a tuning parameter, the temperature will have to vary greatly in order to compensate it and to have a diabatic character, okay, in order for the entropy to become constant. This nice paper was published in Nature in 2019. This was associated to a so-called multi-layer capacitor of this system, and they had seen a large electrocaloric effect into the system with a variation of temperature of about 5 Kelvin. So they have seen that close to this region where the entropy varies greatly, we have where the variation of temperature, the diabatic variation of temperature is greater. And this is very interesting because this electrocaloric effect is performed at close to room temperature. And this is very crucial for technological applications. And not only that, but they have accessed the 1.5 times the entropy associated with the latent heat of the ferroelectric transition. So they tuned this transition to a supercritical regime where they have enhanced the entropy even more, and this large caloric effect was a result of that. And our proposal explains this large electrocaloric effect because it has a lot of entropy contributions, because this is a ferroelectric system, so it has dipolar configurations, it has the multi-layer capacitor or the Maxwell-Wagner contribution associated with interfaces, and we were able to explain these large electrocaloric effects in terms of our proposal. Last but not least in this part, we have given a step further in terms of electrocaloric effects to the so-called quantum paraelectricity. Essentially, we all know that if you get like a textbook, you see that in a paraelectric to ferroelectric transition, when you decrease temperature, the dielectric constant is increased at the Curie temperature. But there are some systems that when you decrease temperature, the dielectric constant is enhanced, but it becomes constant at low temperatures. And this is not usual. This is discussed in the literature as the evidence for a quantum critical point in the system that is somehow locking the dielectric constant, and this is a fingerprint of a quantum paraelectric behavior of systems. So this was discussed very nice by John Barrett in 1952, and he have proposed expression for the dielectric constant in terms of m, which is a parameter is associated to, among others, the dipolar density in this case. T1 is the temperature where this plateau takes place, and T0 is either a paraelectric or antiparaelectric interaction. So this expression gives rise to this blue curve, which is firstly applied to strontium titanatum, strontium barium oxygen 3. Okay, and then if we have the dielectric constant, then we can calculate the electric ionizing parameter. But of course, as the electric ionizing parameter don't have the dielectric constant. But in another recent work of ours, we have proposed that we can rewrite the electric ionizing parameter in terms of minus the derivative of the dielectric constant with respect to temperature. And this made us to employ the Barrett's formula to calculate the electric ionizing parameter to show that in systems presenting this plateau associated with quantum paraelectric behavior, we have a maximization of the electrocaloric effect a little bit above the Curie temperature. Okay? This was another important result. And not only that, we have employed to this quasi-two-dimensional system, kappa BDT TTF2. This is the so-called spin liquid candidate in the literature, the Barrett's formula, and we have seen that the temperature in which this plateau would happen is close to 86 Kelvin, which is associated with quantum critical region. And then we were able to infer that this would be a good area of the phase diagram to perform caloric effects into the system, of course, because of the entropy accumulation as discussed. So these last results give rise to another nice publication in Materials Research Bulletin in 2021. And then I go to the last part of the theoretical section of this presentation, which in turn is associated with condensed matter physics and cosmology. So the universe in cosmology, among other models, is mainly modeled as a perfect fluid, that is, ideal gas. And its equation of state associates pressure with density energy with this equation of state by pressure and density energy associated with a particular constant named omega. And this is what the cosmologists use to model the universe. We can describe the universe expansion in terms of the so-called stress and energy momentum stress tensor, which incorporates the energy density, pressure, shear stresses, and energy fluxes. And then for the ideal perfect fluid, we have this particular version where we don't have, of course, shear stresses because it's assumed that it's an isotropic fluid without viscosity. So for the value of omega changes through the distinct eras of the universe, and this is usually constrained to a numerical value. For the radiation-dominated era, this is 1/3. For the matter-dominated era, this goes to 0. And then in the dark energy-dominated era, which is the current era, which is assumed to be -1. Then what we made here in this part was to associate that equation of state I showed you before with the so-called Wigron-Eisen equation of state. And you can see they are very similar. But then this makes us to conclude that actually this omega is not really merely a constant numerical value, but it also is the so-called effective Wigron-Eisen parameter. And this is another type of Wigron-Eisen parameter that I've discussed in the thesis, but I have not covered this in presentation. But essentially, the Wigron-Eisen ratio I showed you before that quantifies caloric effects represents the singular portion of the effective Wigron-Eisen parameter. The difference is that effective Wigron-Eisen parameter incorporates other quantities like the isothermal compressibility and the specific heat constant volume. So this enables us to conclude that the effective Wigron-Eisen parameter is a summation between all contributions in a solid associated with magnetic, photonic, and electronic, in the same way as omega can be written in terms of all contributions to omega and energy density associated with radiation matter and their energy. So this is the key result of this part, because we have recognized that a parameter that usually constant is actually has a physical meaning, a deeper physical meaning, and this is actually the effective Wigron-Eisen parameter. So Based on that, we have used consideration of a closed spherical model of the universe. We have written the third law of we have written the thermodynamics for this case, and we've been able to see that in the past the universe was expanding in a decelerated way, but nowadays it's expanding in an accelerated way. So we have seen that we have been able to infer that from going to the decelerator to the acceleration era, the effective organizing parameter will change sign, usually what is associated with a phase transition. So we have been able to associate or to interpret this as a phase transition-like effect in terms of the effective organizing parameter. And not only that, we have explored other kinds of equation of states, such as the Shapley model, which is also considers a perfect fluid, but it considers a slightly different equation of states. And we have calculated the effective gamma, and we have seen that for the dark energy era, this is omega, this is assumed as -1. We have seen here that we have a minus, and in order for this to be 1, this term delta R star, which is associated with the parameters from the equation of states, this should be 0, but this is not 0. There are consequences of that. Now, what are the consequences? That for a finite delta, we have that gamma effective is going always to be greater than -1. This led us to conclude that if the universe is expanding, then we have that the volume of the universe is changing, the temperature of the universe is changing, and of course, the thermodynamics of the universe expansion is assumed to be adiabatic. So you have interpreted this as the temperature variation due to the expansion of the universe as a barocaloric effect. And then we have associated that if the temperature and volume of the universes are varying, then probably this omega has to vary as well. And this contradicts the cosmologists in this place, because they say that the so-called vacuum energy that dominates the universe expansion is constant. And we have been able to see that either the cosmological constant or the gravitational constant is going to vary over time. And this is another important result of this part. And then, associating the so-called Einstein field equations, we have rewritten the energy momentum stress tensor in terms of omega, and since omega is the effective organizing parameter, we have been able to recognize the effective organizing parameter inside Einstein field equations. This was another important result, in that we were able to explore anisotropic effects of the universe expansion in terms of the so-called elastic organizing parameter I have shown you before, because it can calculate, it can incorporate all the different stress components associated with the universe expansion. So this gave rise to a submitted manuscript for this part. Okay, now I'm going to the second part of this presentation, which is regarding the experimental section. So the experimental section, as I mentioned, we are interested in the so-called Mott-Hubbard ferroelectric phase. We have the Hubbard-Hamiltonian here. As the first term is associated with the hoppings of electrons from a site I to a site J, according to the annihilation and creation operators. The second term is the so-called on-site Coulomb repulsion. It's associated with Coulomb repulsions between two spins of different orientations, spin up and down on the same site. And then we have the inter-site Hubbard interaction, which is the interaction between two spins in neighboring sites. This Hubbard-Hamiltonian explains the Mott-Insulator transition. When the on-site Coulomb repulsion is close to the bandwidth, or the ratio of U over W is close to 1, electrons localize, so there's a transition from a metal to a Mott-Insulator. And then this can be seen as resistivity versus temperature measurements, where this minimum of the resistivity is associated from a transition from a insulating phase, a metal phase, to an insulating phase. Okay, and this Hubbard-Hamiltonian resolved provides an antiferromagnetic ground state. So why these TMTTF family conductors are important? First, their phase diagram is very rich. So we have here a temperature versus pressure phase diagram. We have here a charge order phase, a metal insulator transition, antiferromagnetic, spin pairs, which is a non-magnetic phase. We have spin-based wave, we have superconducting, and we have the crossover from 1D to 2D to 3D, and of course a metal. And each of these systems is composed by two molecules. That's why it's GMTTF2. The unitary cell is clinic. And then we have the cavities that incorporates a center symmetric counteranion, which can be antimonium fluoride 6, arsenium fluoride 6, or phosphorofluoride 6. And the nice thing about here, the systems are very crystalline because they are synthesized by electrochemical process. And also, if you change this counteranion, you change the so-called chemical pressure on the lattice, and that's why each system starts at a different ambient pressure. Without applied pressure. And this is very important because with this system we can explore various types of phases, and also superconductivity, which was discovered first in the CMTSCF2 PF6 under pressure. Great. So in 1997, it was theoretically predicted that you have at a critical value of the intersite repulsion, you have a charge disproportionation in the systems, and since we have a charge order phase below the multi-insulator transition, and we have a charge disproportionation, we can infer a ferroelectric phase transition. So in order to measure that, as I mentioned in Barrett's formula, the way to do this is to measure the quasi-static dielectric constants, a function of temperature, and of course we would observe a maximum of the Curie temperature. So this has been done in the past for the various salts. We have a symmetry breaking at the charge order phase transition because of the charge disproportionation. And since this is a Mott insulator and it's explained by the Hubbard Hamiltonian and it presents a ferroelectric phase, we have called this Mott-Hubbard ferroelectric phase. So we are interested to see if this particular phase is magnetoelectric or multiferroic. That's the target question. So the motivation for experiments is that this kind of behavior was already being proposed in the literature theoretically in 2015. These guys from the United States and Italy have proposed that these systems are good candidates for presenting a magnetoelectric effect. And then we have the magnetoelectricity of Landau theory, which associates the Helmholtz free energy in terms of the vacuum permeability, the dielectric constant, the dielectric tensor. There is a ferroelectric term, a magnetic term, and there is a magnetoelectric coupling between electric field and magnetic field. Then we can write the electric polarization that it depends on a particular term of the magnetic field, and the magnetization that has a dependence on the electric field. That is, we can change the electric polarization of magnetic field, and we can change the magnetization of the electric field. Okay? So our lab here in Rio Claro we can perform several bulk experiments. As I mentioned, quasi-static dielectric constants, resistivity, thermal expansion, magnetostriction measurements, and it goes from 1.4 Kelvin to 300 Kelvin, and we can apply up to 12 Teslas here. With superconducting magnets, we have all the proper equipment, and I would say that a highlight should be given in the capacitance bridge. We can measure the capacitance by the order of 10 to the power minus 6 picofaraday, with a very precise resolution, which in turn enables us to measure the thermal expansion with very high accuracy, and we can measure length variations below Bohr radius. Of course, we have the equipment of the computer, we have the source to apply currents to magnetize this guy. We have the redundant parallel system that reconstructs the entire system, the entire power supply signal, because we don't want to have any interference from the external power supply in our experiments, because we are interested in very sensitive phenomena. And of course, a lab like this is not plug and play. You cannot go there and press a button and then we will have to start experiments. We have to prepare this, probably no. We have to prepare this one day before, we have to circulate the gas, and then the cool down of the system takes up to 27 hours to achieve temperatures below 5 Kelvin, and then we have a good way to go until the base temperature 1.4 of another, for instance, 12 hours. And then the helium circulation system must be in absence of moisture, and then we have to perform pumping of these with a very precise turbo pumping in order for it to be very clean, because the helium must be high purity. It's more specifically 5,9 helium-4, and then we can see this by when pressure goes to 0, then it means that we are in a very clean environment. Of course, the pandemic and frequent power loss affect the realization of target experiments. My PhD started in 2019, and in 2020 we were all locked down in our homes, and we were like that until 2022. So 50% of my PhD wasn't able to measure. So of course and of course the frequent power losses too, because if this process is cut down the middle, we have to restart, and this means that we have to wait for the system to go up to room temperature again, and so on, so on. So how do we make electrical contacts in the C-star axis? We have carbon paste in the sample. We are interested in measuring the electrical constant in the C-star axis. We're not able to measure in the C-axis because of the triclinic unitary cell. We measure this as it would be a parallel plate capacitor. And then we put our electrical contacts here, and then we put this in the sample rod of the cryostat. This is all made very meticulously, and then we put this inside the cryostat and then decrease temperature and measure everything we want. As I mentioned, we are interested in this particular phase to see if this is either a magnetoelectric or multiphasic phase. And some of the results we have obtained is for the quasi-static electric constant for both the charge ordered for the system antimonium fluoride 6 hydrogenated and deuterated versions. And we have been able to measure the peak in the dielectric constant for the systems associated with the mod-covered ferroelectric phase in the linear regime of the electric polarization. So the next steps are to perform high resolution dielectric constant and electric polarization as well, as a function of temperature, and of course magnetic field to check for the magnetoelectric multiphasic behavior. And also we want to infer for the radiation effects as it has been done in the past. Also, we have performed Raman experiments at the Professor Marcel Dodin lab at UFSCar, Federal University of São Carlos, where we have explored all these salts in context of Raman. Raman, essentially, we have an incident light, and then we have a scatter light. We can be associated with either Stokes, anti-Stokes, or ray life, or even fluorescence. And then we can give us access to the energy scale of the particular vibrations of the molecules of the system. And this is what have been done. And this made us to obtain nice experimental results associated with this particular mode, D4AG, which is associated with the methyl groups here at the end, and of course the double carbon bond here in the middle. And we have seen that upon increasing the magnetic field, we would increase the peak in the Raman intensity for about 27%. And this is a very interesting effect, because this mode is associated with, we have associated with a theoretical work where they have proposed that we have the concentration of charge is higher in this, the methyl groups in this part of the molecule. So we would expect that this would be the more susceptible mode for when we apply magnetic field, and that's what we observed. And this is have associated with a possible magneto-optical effect into this system, which is not covered in the literature yet. And this is an example of this effect for the molybdenum disulfide bilayer. Another aspect we have explored is so-called fluorescence background of this salt. So we have been able to measure the arsenium fluoride 6, the hydrogenated system, in a deuterated system. And then we have observed that the hydrogenated system presents a huge fluorescence background, and the deuteration version does not. And this is, we have observed, but as I mentioned, the pandemics did not make us possible to explore this further. The conclusions and outlooks of this work for the theoretical section is that the local magnetic field must be taken into account in the frame of zero-field quantum phase transitions, or quantum critical points. We have shown a connection between magnetic ionizing parameter and the definition of temperature. We have proposed the realization of adiabatic magnetization by manipulating the local magnetic field, and we have proposed how to detect and how to experimentally attain this effect. Also, we have proposed key ingredients for attaining giant caloric effects, and we have made a connection between cosmology and condensed matter physics through the effective ionizing parameter. For the experimental section, we have explored possible multiferromagnetic character of this chart order phase, which is already still ongoing. We have possible normative relaxation for relative behavior of the salt of the TMTTF2 SBF6 salt due to irradiation effects. And we have the increase of the Raman intensity due to the application of B associated vibrational modes, and also the suppression of the fluorescence associated with the TMTTF molecules due to deuteration. So during my PhD, I had the opportunity to participate in other manuscripts as a co-author. As a first author, I had the opportunity to publish four papers and one submitted. And as a co-author, I have participated in other papers, which is part of the PhD thesis of Mrs. Mello, which is another student of Professor Mariano, PhD student. And then I had the opportunity to participate in many congresses, in 9 scientific congresses through my PhD. And then in some of them we were awarded as best poster or best presentation in these congresses. So I would like to acknowledge the financial agency, CNPq, FAPESP for the financial support, but especially CAPES for my PhD scholarship. Thank you very much for your attention.
Pessoal, nós tivemos aqui uma longa discussão, acho que foram aí quase meia hora, 40 minutos. Discutimos inclusive o seu doutorado e eu pedi licença para o professor Aniakan para falar em português para vocês, para fazer a proclamação do resultado. E eu declaro a partir desse momento aqui que você é doutor, Lucas. Parabéns, está aprovado. Tira foto aí, pessoal. Tira fotos, fotos. Filma fotos, filma.